let's go ahead and get started. I wanted to go to neoswarm.com and share a few more of the videos there and kind of show you what's going on. Um, I think now let's go back to bullies and dweebs, and then we'll get to the gnats. Okay, and then we get to some other sort of swarms. This is the swarm where you have a frenzy bully mob, and we talked about this last time, and we see that the bullies began to get up in drunken mobs and began to attack the dweebs. That's really interesting. And also, what is interesting is the fact that we can actually look at the survival of the dweebs as a function of iteration. And you'll notice in the iteration here, there is a great fall off. So this is kind of a massacre, right? Here's a massacre. It levels off, and then there's another massacre. And we can see those massacres at the end. Until then, there's kind of a gradual decrease, and then there's kind of a diminished return until the dweebs are cornered. Here comes a massacre. There's one of them. There's another one. So we saw the massacres happening. So that's fascinating. And let's watch another one. This is a totally different simulation of the same sort of result. And the behavior of the swarms is due in a function of the initialization. So in this case, all of the dweebs are stacked up right here. You see all of the things stacked up, and here are the bullies. And so what do you think happens if all of the dweebs are stacked up and all the bullies are stacked up? I would think that the bullies would just get the dweebs and massacre them initially. But that indeed is not what happens. Let's look at what happens. You can see that the dweebs have a chance to spread out, and this breaks into a steady state wherein it's just like the random distribution of the dweebs and bullies in the beginning as an initialization. So we have a similar sort of thing, and even though they started close to each other, it turns out that the dweebs were able to appropriately spread out. You'll notice, and I keep mentioning this because it's kind of interesting, is that most of the killings are at the edges or the corners. So we can see there's a gradual degradation. In this case, we see that there's a massacre here and that there's a massacre here as things line up against the wall. And here comes the final touches, the fine tuning when they got all of the dweebs. Now, here's something even more interesting. It's the same thing where all of the bullies are stacked in the corner and the dweebs are here. You would expect that it would be the same, but this one is a short video and is actually kind of funny. And you'll see why it's funny in a second. Notice that you start rooting for the dweebs in some sense. Notice that there's one dweeb that survives the massacre, and all of the bullies are after him. So it's a big massacre at the corner as the bullies chase the dweebs, and apparently the dweebs aren't able to spread out as much. The bullies come in, and there's one little one little dweeb that is escaping the bullies. I don't know. I look at that and I chuckle. It's amazing how we anthropomorphize things. We're kind of looking at this as a sports contest or something like that. So we can see that, yeah, things are really, really good till they reach the corner. Then there's a big massacre as they kill all the dweebs, and then it's kind of a steady state. So that's bullies and dweebs. Ah, there it is, war games. One of the things that happened was that we took the bullies and dweebs scenario and we evolved it. We applied evolutionary computing. We'll talk about evolutionary computing in a little bit. But basically, the idea is you take a number of swarms, all defined by different parameters. You implement the swarms, and then you see how long it takes to kill the bullies. Well, you can't wait until to kill all the dweebs. You can't wait until it kills all the dweebs. You actually have to do something else. So we just waited until it killed half the dweebs, and we figured out that was the fitness. So the longer time that it took to kill the dweebs, the better. That was the fitness that we were after. And if we were after that fitness, we would generate a bunch of different swarms with different parameters. Then we would take the ones that were the weakest, the ones that lasted the shortest amount of time, and we would kill off maybe half of them. And then the other ones we would duplicate. Then we would go back and we would mutate them a little bit. In other words, change the rules a little bit, and then do it again. And we would kill off the weak. We would duplicate. We would mutate. We would kill off the dweeb. Kill off the weak. Duplicate, mutate, and do it again and again and again. And this case, we were trying to maximize the lifetime of the dweebs. And what was fascinating is that in one of the cases, the dweebs were able to recognize that the killings occurred at the corners. And because they occurred at the corners, the dweebs began to avoid the corners and began clustering in the middle. And this is what happens. You can see all of the dweebs are clustering in the middle because they don't want to go to the edges because that's where all the killings occur. So this is the process of evolving, and this is the way that the dweebs get a long time for their swarm to survive. So as long as one dweeb is surviving, we say that the swarm is surviving. So we go to the last dweeb here. So you can see they gather in the middle and kind of taunt the bullies and try to keep away from the edges. But eventually, as the bullies choose a dweeb, they force it to the edge where the killing occurs. But usually the bullies go to the corners and kind of try to hide there, but not in this case. So this was one of the results of the evolution. It turns out to be a false minimum. We can do better than that. So you can see that the things are lasting for a long time here. The swarm is lasting for a long time because the bullies have to go to the dweebs in the middle, choose one, and then corner it in a corner or a side, a boundary of the killing field. We also did some interesting stuff where we took this one and then we began to evolve it with the bullies. How could the bullies overcome this way of evasion? And I'm not going to go through that, but notice that you can go back and forth. You can optimize the dweebs and you can optimize the bullies, optimize the dweebs, optimize the bullies, and see where that takes you in terms of optimality. It's a fascinating way to do things. I think that the most compelling way to maximize the life of the dweebs is through this emergent behavior as a result of evolution. And this is really fascinating. Let me show you why. Here's bullies and dweebs after a number of times of evolution. And here's what happens. One dweeb turns out to go to self-sacrifice. And this dweeb goes around chased by all the bullies, and all of the other dweebs kind of hide in the corner. And so this dweeb that is going around in circle is sacrificing itself. Now, eventually, the bullies are going to catch up with that dweeb and get it. But it's got to chase it for a heck of a long time. And again, remember what we're trying to do is maximize the time, uh, the time for the swarm to survive. As soon as the dweeb is killed, there's kind of a chaos, and then in steady state, it breaks into again another dweeb sacrificing itself for the entire swarm. So this was really surprising. Once you see it, you say, "Well, this makes sense because what is that? What is that dweeb doing? It's chewing up time, and we want to maximize the time of the survival of the swarm." So it's doing very well. And again, it breaks into chaos, and then it comes over and begins to attack again. Pretty soon, one of the dweebs will be identified for self-sacrifice. There's a self-sacrificial dweeb, and he's going to run around in circles and chew up the clock in order to maximize the lifetime of the swarm. So I know of no place where this happens in nature, but if we were doing some other sort of swarm, not in nature, we would see that self-sacrifice is something which works very well. Okay, there they got the dweeb, and therefore things scatter, and we get again another sacrificial dweeb. All the other dweebs hide in the edges and in the corners, staying away from the bullies. And what is interesting about that is we did this with disjunctive fuzzy control. And that just means, if you remember, for disjunctive fuzzy control, it corresponds to an actuator function. And that actuator function is something that can be tuned because the actuator function is usually construed as piecewise linear. And so we just had to tune all of the different places where the breakpoints occurred in the piecewise linear curve. And once we got to this result, the person that did this, a guy named John Roach, did very interesting work on the evolution of the swarms. Uh, he looked at this and he looked at the actuator functions that we ended up with, and he says, "Oh my gosh, this is the solution." Now, was the swarm evolution creative? No, we gave it a billion different possibilities corresponding to the different actuator functions. And it was able to choose from this billion the actuator form that gave the self-sacrifice. And he looked at the actuator functions and he said, I can see what they're doing. And this is in a paper, and you can look at the paper and see what those actuator functions were. So we're down to the last, no, I got the last two dweebs, but they have been sacrificed one at a time in order to maximize the lifetime of the swarm. And again, if there's one dweeb left, then the swarm still survives. Oh, I guess there's still another dweeb. Okay, notice that dweeb kind of goes towards the bully and then goes away from it. Oh, okay, now we're down to the last dweeb. So we have thinned the herd and we have maximized the survival time of the swarm through this process of self-sacrifice, which was discovered among the millions of different solutions that we offered, millions, maybe billions, of the different ways that swarm could survive. So that is the application of Oh, no, I guess there's still more. I guess they were hiding. Okay, you've probably seen enough. Self-sacrifice. So remember, if you want your swarm to live for a long time, sacrifice yourself. Let's see, does this thing go to the end? Oh my gosh, it's not even halfway done. he's sacrificing himself because as long as he's alive, the swarm is said to be alive, and he's maximizing the life of the swarm. Notice in this evolutionary computing that we have a goal, and this goal is to maximize the lifetime of the swarm. And that doesn't happen in Darwinian evolution. There is really no goal except maybe to populate the earth or something like that. And and so it is not happening just by random undirected mutations. Okay. So I thought that's fascinating. So what we've done is we've seen that initialization of the swarm has something to do with how it performs. And if we lump all of the dweebs and bullies together and separate them, it turns out there's a massacre, except for that one little dweeb that kind of gets away. That one little dweeb that gets away is, I don't know, I kind of find it funny. And I kind of find it funny that we actually look at this as a sporting event. That little dweeb is surviving. So he's the underdog. So we kind of root for it. Okay, so that's all I wanted to say about bullies and dweebs. There's some other videos here if you'd like to look at them, and and they're the result of evolution also, the evolutionary search, if you will. So let's return to what we talked about last time, and I challenge you to, for the case of gnats, to determine what the rule was that made things look like gnats. And this is what it looked like. Okay, so what happens here is that if you figured it out, it's at Neoswarm, but you can see occasionally that a red circle appears for a gnat. So a gnat kind of moves in one direction with a little bit of twiddle, a little bit of randomness, until that until that gnat becomes the farthest away from the centroid of the swarm. And when it becomes farthest away from the centroid of the swarm, it gets a little red circle around it, and it turns around and goes back towards the middle of the swarm. So that's the simple rule. Random search. Actually, it's just a walk in one direction with a little bit of twiddle on it. And if you get to the outmost edges, the graphics here draws a little red circle around it, and you head back in the direction from whence you came. And that's enough to give this very kind of spooky looking thing, which is the gnats. I don't know. I don't believe that the gnats look that way. And then we also talked about the emergence of the kind of the radius. These are the outliers. These are the maximum deviations. In other words, each of these points correspond to when a gnat is on the edge of things. And so you can see that some of them are really far apart, but there's kind of a mean here of a 1.6, okay, times 10 to the fourth, but a 1.6. And this was 100 gnats. In a similar sort of situation, we started the gnats all in a circle, and we showed that they, as an emergent behavior, they kind of got larger and larger until they kind of had the radius of the original circle that we started out with. And we can see that indeed this is the case, that the radius of the circle begins to increase in a stochastic sort of way and reaches a steady state, which is the circle of the original gnats. So in steady state, it goes to that original circle. Then we also saw that if we dispersed the gnats, that they also converged to the circle. So here are the gnats converging to the circle. So that's an interesting behavior based on the simple rule that if you are the farthest away from the centroid of the mass, then you have a red circle drawn about you and you turn around and go in the opposite direction, 180 degrees. Okay, worm search. Here's a little background on worm search. Okay, here's the idea. You are running a underground submarine searching, autonomous, that is trying to find other enemy submarines. And what you have is a certain area that you would like to explore. And you begin to go around and you begin to explore this area. And as you explore the area, well, there's a bunch of agents going around and exploring the area. And what we would like to do is to make sure that there's no enemy submarines. Now, it turns out that underwater, you cannot use things like radar because electromagnetic radiation goes through water like a laser goes through chocolate milk. It just doesn't penetrate. That's the reason that they use sonar. But sonar can be a very small radius, and we don't want to have the ships be equipped with sonar because sonar is detectable, just like radar. I was on a podcast the other day and they were talking about autonomous vehicles and warfare. And one of them is the Israeli Harpy. And it is a missile which goes above a predefined area and it circles that area. They call it loitering. It loiters over the area until it's illuminated by radar. And as soon as it's illuminated by radar, it zooms in on the source of the radar and goes in and takes out the radar installation by a kamikaze attack. So it destroys itself getting there. Um, well, that's also true of sonar. If you're pinged by sonar, you should be able to triangulate and figure out where the source of that sonar is and go away from it. So we'd like to minimize the use of sonar in this detection. One other thing happens is that once you search an area, that as time goes by, that area becomes more and more, or it's less observed. And it could be the enemy sub snuck into that area after you explored it. And that probability begins to increase as time increases. So if you've explored one area and you've left it, there's a greater chance that that can be occupied by a submarine in the steady state. And so you got to make sure that you even revisit some of the places. So here was some of the work that we did for the Navy on doing that. Um, let's look, for example, at this case where we have a bunch of drones, if you will, autonomous drones exploring the bottom of the ocean. And the idea is that they go in a linear fashion and they bounce off the boundary of the search area, and then they do this. Now you can see as the drones move that the colors behind it in its path, they begin to change, don't they? The colors in the path begin to change. And that means that the probability is decreasing that you're certain about that area. You'll notice that this isn't very original because what happens is that the drones, if you will, that are doing the exploring simply bounce off the wall. Okay, so that's it. Well, you can see that there's some unexplored areas here, and these unexplored areas are places where if just by chance the submarine hid, that they wouldn't be explored. So, and the other thing is that all of these paths are deterministic. And if you're an enemy and you have the wherewithal, you can literally figure out where every drone is going to be at every time. And they just bounce off walls. And maybe that can tell you where a good place to hide is. So let's do something else. Here, what we're going to do is we're going to add a little bit of randomness, a little bit of twiddle. So they not only move in a line, but they have a little bit of twiddle, and that little bit of twiddle gets them a stochastic sort of result. So what happens is that this will prohibit an enemy from figuring out where you're going to be in the future because of the stochastic nature. And that is probably a good thing. Okay, so this does, It's kind of an okay job. The next constraint we added, um, besides the idea of stochastic, is we included repulsion. What does that mean? Well, these underwater drones, these autonomous vehicles, submarine vehicles, are not using sonar, but they can detect if they bump into or get really, really close to another drone. So it seems that if they do that, they shouldn't go on in a straight line. They should actually move their line, move their direction, and that's what happens here. So this is what we called repulsion. So if two drones hit each other, they go in a like a 90-degree path from each other. So that's all well and good. And with repulsion, we get I don't know how good of a result that we get here. But what we can do is something interesting. We can put them all together. In other words, have repulsion and have the stochastic measure, which we didn't have. And let's take a look at this. So this is repulsion with the stochastic aspect to it. So the coverage is actually better using both the repulsion and the stochastic. What the repulsion does is keep the drones from covering freshly plowed ground, and the stochastic randomizes it up and does a better job of not allowing prediction of where the drone is going, and also it allows better coverage. So you can see that we're having a better coverage here. And it turns out, just like with anything, with this, we have different parameters. There's a trade-off between the repulsion and the stochastic. Now, here's the problem with all that. The problem with all that is that in sonar, your ability to cover a large area is determined by your environment. In sonar, things don't travel straight, for example, because you have things such as sound speed profiles, where sound travels more quickly beneath the ocean, close to the ocean floor, because the water is denser and sound travels more quickly in that way. So sonar actually doesn't go straight, it bends. And then you have other operations. So here is the old question of searching under the lamppost. Suppose that you are in a parking lot and this big square here corresponds to the parking lot, and you've lost your keys and you want to find your keys. If you want to if you want to increase the probability of finding your keys over a short period of time, you spend all of your time searching under the lamppost, right? But if you really want to do an exhaustive search, you have to come out here to the darker area away from the lamppost, and you need to look at things more closely. So the idea with the drones is that over here under the lamppost, the circle of the drone is really large because it can look at a large area. Over here, the circle of the drone is going to be very, very small, so you can only look at a small area. So if you want to do an exhaustive search, you have to not spend all of your time searching under the lamppost. You have to spend some of your time searching in the dark here. So let's see how that works. And this is the profile that we're using. You notice that the circles on the bottom right are larger than the circles on the upper left. The bottom right circles are bigger than they are on the upper right. And that's because you have better surveillance there. But this is just application of the previous algorithm where we have the repulsion and we have the stochastic nature both going for us. But you will notice in the upper left, far away from the lamppost, we're not getting very good coverage, are we? And that's the reason. The reason for that is the chance of searching far from the lamppost and searching in the lamppost is actually going to be exactly the same. And therefore, searching away means you're not going to cover as much area. So you're not going to get as good area on the upper left as you do on the bottom right. Look, the bottom right looks very well searched. It's almost solid red and orange. So if we look at the average of this search over time, we get something interesting. So let's take a look and see what happens here. So therefore, we see that on the average of time, the search on the bottom right looks very good, but the search on the upper left looks terrible. And this is commensurate with the idea of looking under the lamppost. We can see a lot looking under the lamppost, but we can't see a lot in the dark. So if we spend equal time searching under the lamppost and in the dark, well, we have to take the consequences of that, and that means that we don't search away from the lamppost as much as we possibly should. So this behooves us to ask the question, how can we search more in the dark here? How can we search more in the dark? And the answer is to add another component to the stochastic search. And the idea is that if the circle is getting smaller, and notice every drone can determine the area that is covered, that if the area is getting smaller, then it's going towards a darker area. If the circle is getting smaller, it's going towards a darker area. And if the circle is getting smaller, we want to encourage movement towards that darker level. So we put that in there, not as an absolute, but as a weight in the direction of each one of the little drones. And let's see what happens then. Now we have an attraction to the dark level, to the dark side, if you will. And this is what happens. And you can see you can see from that color map that indeed we're doing a better job in the upper left-hand corner. It's still not as good as the bottom right. The bottom right is still orange if we look at the average search over all of the time. But nevertheless, it's better. It's better than it was previously. So maybe we would like to have a little bit more attraction to the dark area. In other words, if the circle is decreasing in size, we want a greater weight towards attraction to the upper left. So we turn a little knob on our optimization algorithm, and we get the following. Okay, so you can see that it's a lot better, but as the color map says, we're getting a better search in the dark area, but at the sacrifice of a search in the well-lit area. I don't have the swarm for this, but if you tune the knob back a little bit, you can get actually coverage like this, which looks fairly uniform. It looks fairly uniform. Now notice what we've sacrificed. This is a trade-off. We are searching, and the yellow says, yeah, we're searching kind of consistently across all of the different locations in the parking lot. But notice at what sacrifice. Up here, we had really good coverage in the corner, and all of that orange and dark red shown here has been sacrificed. All of this became yellow so that this became yellow out here. It's kind of like it's sand in a sandbox, and we got to figure out how to spread that sand. And the sand on the right correspond, or in the bottom left, bottom right, the sand on the bottom right needs to be spread out. It's heaped up, so we have to push some of that over to the upper left. And that's what happens for this choice of trade-off between the stochastic and the attraction going downhill. And here we've done too much. We go downhill too much. So that's kind of crazy. Here's what happens if you go to the extreme and just spend all your time looking in the dark. Here's a case where the downhill really is astonishing, and you can see that all of the little bugs are spending their time in the upper left because they are attracted to going downhill. But in doing so, you totally ignore the search on the bottom right. So this is overkill. So we have a knob which we can turn, and it depends on what you want. If one wants a totally uniform search, one would actually use this dr is equal to zero point 0.1. To know dr, you have to go to the code, and I think the code is supplied on the screen if you'd like to look at it. Okay, so that's not good. To the code, and I think the code is supplied on the screen if you'd like to look at it. Okay, so that's not good. So that's one of the profiles. We also looked at other profiles. A lamppost here, a dimmer lamppost here, and dark in the middle. What happens? Well, you can see it's really dark in the middle. So when the bugs go, or when the drones go in the middle, those dots are really, really small, aren't they? So that means in order to get coverage there in the middle, we're going to have a lot of little dots going going a long way. We have to have a lot of those little dots covering that center. And you can see with this case where we don't have any attraction towards the dark space, that as you can see in this color plot, that you get a lot of ignoring of the dark space of the search. And that's what we would expect. So again, we can turn the knob a little bit and have more attraction towards the dark spot by seeing if the circle gets smaller or not. That actually improves it a little bit, as you can see from this color map. But still, we have places which basically remain unsearched because it's really, really dark there. It's really, really dark as measured by the diameter of the sensor as it goes through the dark spot. Okay, well, you know what? This is kind of a pile of dirt, and we have a lot of dirt here in the red, and a lot of pile of dirt here in the red at the bottom left, and we have to shove that dirt in to cover up the hole, which is shown here in the middle. To do that, we do more attraction, and we get this result. And you can see this result isn't much better, where that attraction is turned up, and there's even more attraction. It's a little bit better, but we still have places in the middle where things don't work out. Well, let's go to the next obvious place. This is another case where we put where we turn the attraction to the middle a little bit more. It gets a little bit better, but you know what? It still kind of ignores the middle. I mean, that middle is really dark. So we have to spend a lot of time there if we're going to exhaustively search for your keys. And here it is a little bit more. I want to pause this not to eat up my bandwidth. And here it is with a little bit more. It's getting better in the middle, but notice the dark red on the corners are being diminished. So again, what we've done is we've tuned the swarm to be more attracted to going downhill, to going towards the dark. So it's not like when you die and you look at the light. Here you want to do your thing and look at the dark and go towards the dark, spend more time in the dark. Okay, well, we got to crank it up even more. What happens if we crank it up even more? Well, we still don't get it. You can see it's a lot better, but that bright red that used to be on the corners now is turning kind of orange and yellow. So we've pushed some of that dirt over, but there's still a lot of gaps in the dark place. So push it a little bit more. Guess what? Okay, still not good according to this heat map up here. But notice again, all of the red is going towards orange and yellow. Finally, we get decent coverage, but at what cost? If we want decent coverage, as we see here, we've kind of gotten rid of the all of the red, all of the good surveillance, and we're actually not. We're staying away from where it's well lit in the upper right corner. But that's the price that we have to pay using this particular algorithm. And if we turn it up too high and spend all of our time looking at the dark place, we get the following result. Here, you're really attracted towards the dark. And because you're attracted by the dark, you spend all of your time looking at the dark and you ignore the light areas. So here we're attracted to the dark area and spend a lot of time looking at the dark area. And as you can see by this average over here, that yeah, you're really exploring the dark area at the ignoring of the light under the lamppost. Notice that all of this can be done in a exhaustive search. In other words, you can take this parameter, which is the degree that it's attracted to the dark, and you can just fiddle around with it, run all sorts of scenarios, get this heat map, and decide which one you want in the heat map. So this is something you can do in a simple search, in this case, probably exhaustive search. That's some of the stuff we did for the Navy. I'm sure you're tired of looking at some of these swarm videos. So next time, there's one other example, very short, that I want to go through, and that is based on the book Ubiquitous. And it talks about the idea that there's this one curve that occurs quite a bit called the power curve. And we're going to look at that, some of the consequences of the power curve, and then we're going to try to emulate it. So we'll see. Okay. Great. Thank you very much.